So for the recording, I will make the PPT only share. Good afternoon, friends. Welcome to the third session of ARM-based development. This course, in this session now, we will be covering the reset and register set portion of the topic. So the following are the subtopics that we would be covering in this presentation. What I would like to do in the initial first few sessions is that you understand the basic memory interface and then the basic architectural features, so that when we get into the assembly instruction level details, you have all the background knowledge what is needed, especially from the ARM architecture perspective as well as from in general about the processor architecture. So you are well equipped and prepared to understand the assembly instructions and understand deeper details about how it is implemented and how they are used in different scenarios. So in this session we are going to cover what is the nomenclature that ARM uses, what is the processor core and what is the CPU core, and then we will talk about some of the key interface signals that comes out of the ARM processor core, then how the memory is interfaced with the processor core and different bus cycles that ARM support, then the register set and different operational modes that ARM supports there. And let us touch upon the reset behavior also, because that's where the processor starts executing your instructions, and once we understand this, then we are ready to get into deeper about instructions. Okay, let us carry on with our flow. So let us see what is ARM7TDMI. So this is the processor core that we would be covering in detail, especially for the assembly instructions. So we should be able to understand, if the name is given like this of ARM core, what each of these letters mean. So I have given only for this particular processor core what these names imply. 7 is one series of instruction set architecture that ARM has come up with. So ARM has started with 1, and what we are studying now is the 7th series in the instruction set architecture of ARM. And T means that it supports thumb mode. As I have mentioned briefly in the earlier discussion, that thumb mode is a 16-bit instruction bit mode. This is for a compressed code execution, where there is an embedded system where we have very high limitation on the memory that footprint of a code that we can use. We can go in for thumb mode where 16-bit instructions are put in the ROM, and that is read by the processor, and it is expanded, decompressed, and then executed in the processor. So we will not touch upon this now. There will be one session dedicated for thumb mode. So just thought I will let you know what it means. D is a debugger unit. It is present in the processor, so that person, as a developer, we can run our code on the target platform, and then we should be able to debug our code by single stepping it, executing one instruction after the other, and see the contents of the register, so that we can understand how our program is running on the processor, and if there is any bug in our code, we will be able to fix it. So processor supports debugging by providing a separate hardware unit in it. And then multiplier unit and embedded IC is for a built-in debugger hardware. So these are all for, these two are for the debugging perspective, and this is for high performance multiplier unit present in the system. So we will go into these details later. This is just an introduction about the naming convention and the nomenclature followed by ARM. Now, what is the processor core and what is the CPU core? See, when we see ARM-based SoC, it is already the ARM processor core is inside that chip. SoC is a system on a chip. So we have a processor core. It could be ARM7 or ARM9 or ARM10. and that processor core is bought from ARM. So this is the contribution from ARM unit, ARM company, and then it could be integrated with the instruction cache or data cache and MMU that also is provided by ARM, but that comes as a separate unit. So ARM interface. So the whole thing, when you have a bus interface and the cache and memory management unit, this all of them go into a single chip, which will be a CPU. When you say board, development board with an ARM CPU in it, we will call that ARM CPU as one of these things, ARM710 or ARM720 or ARM920. So this kind of CPU contains the processor core inside. When we talk about instruction set and different register set and different modes, we are talking about what is inside this processor core. And when we talk about different signals coming out, these are all the signals coming out of this processor core, which is integrated with the rest of the unit and built as a single chip. So I hope this makes you understand the difference between a processor core, which could be ARM7TDMI or ARM9TDMI or one of them, and then the CPU core along with the different cache memory and other functions what is required in the SoC, they all combined together called as a CPU core. So the other units that are used along with the processor core may not be from ARM. It could be from third party, or it could be the module coming from the vendor who bought the ARM IP and integrating it with his own coprocessor and then building a chip which will be used for a particular end application. It could be for networking, or it could be for data processing, or it could be for graphics. So this is how ARM vendors buy the ARM IP core from the ARM and build a system. Now, if you see the name like this, you should remember that it is a processor core. Now, these are the signals coming from this 7TDMI processor core. You may wonder, where are the pin numbers? Because we are all used to seeing a processor core with the signals input output, so going out and some inputs coming into the processor. We are used to seeing some pin numbers along with that. But here what you see is only the signal description. Which are the input signal and what are the output signals, and what are the different kinds of signals that go into the processor and grouped based on the function. Now, why are they not giving any pin numbers here? Again, the reason being, this is not coming as a single chip. This is a IP, again intellectual property code, which is going into some other SoC. So these signals will be going into some other modules within the chip, and then those signals come out of the IC. So those pin numbers, it could be anything. So it is independent of what is coming out of this core. So that is dependent on the vendor who bought this ARM core and built an SoC. So when ARM is giving the description of the signal, it doesn't talk about the pin numbers. Hope you understand this. Why there are no pin numbers in this description. Now let us see what all this. High level I will show you some signals, but we will not go into the detail of signals here. But as soon as as and when we cover some part of the modules, we will discuss about each signals also. Okay, as we move forward. Now, one thing what we should remember is that when the processor is powered on, it has to start from some no state. That is, a processor needs to get a reset signal. So there is a pin input signal going into the processor core, which is a reset bar. It is represented as n reset, or in a signal description it will be shown as a reset bar. So once here what happens is when the signal is low, it is active. So what happens when the reset signal is activated, the processor starts executing the code from the address 0x or 0. So this is the hexadecimal notation of address. So I have given this many zeros because it's a 32-bit processor and the address range is 32-bit from 00 to all x. Now, what is the clock going into the processor? So any processor needs the clock. So in the ARM processor, we call it as M clock, which is actually for a memory cycle clock. This is could be coming from the external circuitry. It could be a crystal, or the crystal may be connected out of the chip, or it could be generator, multiplied. So whatever may be the modifications or changes going to this clock, what is coming into this is M clock, which is based on which the processor is running. Now you know that this is a 32-bit processor, so address bits are 32. They connect to the memory. Now ARM processor has a unique feature where it has got two types of databases. I will talk about this later, why it is required and how it is implemented. There are so many control signals. Of course, you know that for any memory cycle there must be some read write signals to be going on, and then other request kind of what is the bus data which is being read or returned into memory. So those control signals are going out from these signals. Now in the earlier session I mentioned that ARM is a bi-endian processor. What does it mean? We can make the ARM processor run either as a big endian in the big endian mode or as a little endian mode. So based on the signal given to this input, it will behave as a big endian or little endian. So you may wonder whether the signal needs to be always constant. Of course, if the software running on the chip is always assuming that the big endianness is followed, this should not change in between. Otherwise, you will see the performance totally, it won't work at all. So totally. But if there is a requirement that this needs to be switched from little endian to big endian because of some application requirement, that is left to the programmer and the system designer to take care of it. But from the processor code perspective, it senses this signal. If it is 0, it behaves like little endian machine. Otherwise, it behaves like a big endian machine. Now, any processor has to have some interrupts. So all of you must be aware what the interrupts are for, which is to indicate what is there any action that needs processor's attention. Those interrupts will be generated by these signals, and they are connected to two input signals, which called IRQ and FIQ. I will talk about that later. Fast interrupt and interrupt response pin. Then there are other descriptions, a whole lot of signals which we will not talk about it now. As and when there is a need, we will talk about that. Okay. Let us go to the next session. Clock signal. I mentioned that M clock is a memory clock which is going into that. This is all state change within the processor are controlled by this clock. This is the main clock for all memory access and processor operations. Now this M clock has a provision that we can slow it down to make the whole processor run slow. If suppose slower peripherals or memory needs to be integrated with the processor. So you may wonder why this kind of flexibility is given in ARM, because when the ARM IP is made, it could be integrated with any kind of system. It could be with a fast clock, processors with a fast clock, or it could be integrated with the memory and other systems which are very slow because power requirements are less, and which is for a low end application. Then the processor should be configurable to run in any speed. So M clock has a provision with the additional signal called N wait. You can always set the clock signal to make it run slow. So the internal clock is always taken from M clock signal and with N wait. So any clock will be having a high pulse kind of a thing. I will show you the description of this clock. And when N wait is added, if it is low, the clock is frozen as kept as low. So only when N wait is high, that is 1, the M clock is taken in as a clock and the processor is running with that speed. So if you want to stop the processor or stall the processor, make this N wait low when the M clock is low, and then you keep it as long as possible. Whenever you want that again for the processor to run, you can make this N wait high, and then when the M clock becomes high, the processor starts running. So this is another output pin coming out of the ARM processor code to just see what is the internal clock of the processor. So this is actually E clock is the output of these two signals which were fed into the processor. Now this, as I mentioned, n weight signal is used to set the memory cycle if slower memories are in use. So this is all about clock signal. Now I mentioned that ARM7TDMI is a one Neumann architecture. What is one Neumann? We have a single memory for both code and data. Now, so there is only one address bus connected to the memory, and there are some control signals apart from MREC and sequential access. There is a MEAS address. This signal gives you what is the kind of transfer. I will explain this in detail in the next slide. So now you see here. Now when this bus enable is given at 0, then ARM processor is connected to the memory through this data bus, which is a bidirectional bus. So what happens? Both while reading as well as writing, the data flow through this bus. If bus enable is 1, these are the pins which are activated, and there is a separate data in and data out bus. So having a separate data in and data bus doesn't mean that it's a forward architecture. We need to have a separate memory and separate address data bus, then we can call it as a hardware architecture. This is simply again same one Neumann architecture, but only thing is the data could be multiplexed or it could be separate for input and output. And you know the range of addresses are 32 bits, so these are the maximum range of the addresses for the memory. So both code and data reside here. So when a process is running, it has to use the same address bus and the data bus to read the instructions as well as read any data that needs to be read in or written into through the same bus. So you know that these two cannot happen together. Now why do we need this? In a typical environment where we want ARM code to be connected to a external memory, a bidirectional bus is used normally. But if it has to be connected within some internal circuitry, some in the SOCs, people can make use of these two buses for accessing the memory. So only at a time, only one of them can be used, and it is the system designer's choice whether to drive this pin as 0 or 1 and then use the appropriate data buses for interfacing with the memory. So this kind of flexibility is given again because the ARM code is given as an IP, and it can be integrated with any other processor to build an SOC. Now, how is the memory access happen in the ARM? Address bus provides 4 GB of linear address space. You know the 32-bit maps to 4 GB, and the processor can transfer either word or half word or byte quantity. So as I mentioned, this memory which is used is a byte addressable memory. So ARM can transfer any of these data bits from the memory, or it can write any of these 32-bit or 16-bit or 1 byte entity. So who decides that the MEAS input is a 2-bit input coming into to the memory? Actually, it is driven by the processor. So this encodes the size of the transfer. So if a processor is transferring a half word, it will put in a proper combination of bits to indicate to the memory that I am transferring a half word or a byte or a 32-bit whole word. So based on this signal, MEAS signal coming out of the processor core, the memory understands that the transfer size is one of these three, and then accordingly it reads the data from the database. However, the memory system must ignore the bottom redundant bits based on the transfer. Let me tell you, if suppose it is processor is driving this 10 as a combination, that means it is doing a word transfer on the database. That means for a given address, there are 4 bytes of value which is either coming out or to be read from the memory by the processor. Now, as you know, the addresses are byte weight, but this 32 bits indicate that there are 4 bytes which are read or written and a single memory cycle. Because of this, the bottom 2 bits are redundant, because assume that 1000 is the address. You have read 4 bytes. Now what will be the next address that you need to put it on the memory? It has to be 1004. That means you are jumping, the address is jumping from 1000 to 1004 to 1008. That means the intermediate numbers, that is 01, 0001 and 10 and 11 are not coming out of the address bus, because address is incremented every 4 bytes. So because of this, the bottom 2 bits will be ignored if it is a 32-bit access. If it is a half word access, you understand that 1 bit is redundant, but if it is a byte address, all 32 bits are valid addresses, and that needs to be understood, and accordingly the memory has to act on it. So in summary, ARM supports all kinds of transfers, both input as well as output. It can write into the memory in any of these word sizes, or it can read from the memory also in any of these word sizes. But when it is doing, it has to inform the memory that what kind of transfer size it is performing for a memory cycle. So this can change from one cycle to the other cycle. Every memory cycle can decide whether it wants to do any of one of these transfers, and based on this, these bits are driven, and the memory needs to support this. Now let me give an example. Okay, let us take an example of this particular combination, that is A1 of 0, this MAS address bit 1 and 0 is 0 1. Okay, byte read on 0 1. That means here this is a address bit 1 and 0. So once you are reading a byte, that means all the bits in the address are valid. So if the byte is showing the 0 1, that means it's an odd byte which is read by the processor. Now you have to remember that based on the little endian or big endian, this could be mapped to either 1 byte from MSB, or it could be the byte next to the LS byte. So what I am saying is, based on the endianness of the processor, this signal what is given, the byte what is being read or written into is taken from the respective data buses. So if it is a little endian, you know that LS byte will come from this part of the memory. Whereas if it is a MS big endian machine, it will be, the value will be coming from, if it is a lower byte, it will come from the MS byte, because it is stored as a higher address, right? So because of that, what happens is, wherever the byte is read is coming on whichever data bus, it is copied into the lower byte of the register, and then there is a sign extender, or it is filled with a 0 based on the kind of transfer which is being done. So basically this helps in terms of transferring a word or a byte or a half word from the memory, whatever may be the endianness, and then transfer that value to a particular place in the register. Now let us see what happens when a memory write is performed. So this shows that LS byte is coming to the LSB here, data bus. So this is a little endian mode. Then what happens is, this data, if it is a word write, it comes on all the 32 bits of data. But if it is doing a byte write, that is, the processor is trying to write one byte, this byte, particular byte of the what is there in the register into the data bus. So it copies the same byte into all the 8 bytes of the data bus and writes it. You may wonder why that single data is copied onto 4. This is just a provision given, for the memory to use any one of this based on its convenience. Okay, but actually only 1 byte is getting transferred, but it is, instead of leaving these other data bus pins empty, they are driven by the same data, so that the memory could perform you can read any one of these bytes to copy into its location. If it is a half word transfer, then it is given on to both the 16 bits of the data bus. So this is a way memory is getting written into different words, the word widths are written into memory from the processor. So can use the most convenient copy of the data. Okay. Now let us talk about the bus type. We call this processor bus interface as a pipeline. Now what does that pipeline mean? It gives maximum time for memory to decode the address and respond to the address request. What it means is the address will be given ahead of the memory supply, and the memory has a sufficient time to decode the address and put the data back into the data. So this kind of pipeline mode is particularly useful for DRAM because DRAM has a row and a column addresses, and it has to resolve a particular cell in the DRAM memory and then get out the value. So it takes some time for decoding the address and then putting the data out on the data bus. So in the pipeline mode, the advantage is that the address is given ahead of the memory cycle, one cycle before, so that the decoding can proceed from the memory side and it can be ready with the data, and when the processor can read it from the data. So this is what is address expressed in this, and then in this mode, the address bus does not remain valid till the end of the memory cycle. So there needs to be a agreement between the memory and the processor, the signal details, and then accordingly the address and data bit will be read by the processor. So there is an address pipeline enabled signal which indicates to the memory that it is in the pipeline mode. In the deep pipeline mode could be used for SRAM and ROM kind of memories where this kind of a delay is not needed from the between address and the data reading into the memory. Now I'll tell you a small, I'll show you a small bus cycle here. This is the M clock which I showed you that it is driven from the external circuitry into the processor core. So this this is a complete one cycle here. So what you see here is it is a pipeline mode because this is high signal. APE is address pipeline enabled, and MREC and SQ sequential is a combination which gives you whether processor is in a sequential mode or in a what kind of a bit of address it is being read. Now address is coming out here and the data is read on this particular falling edge of the M clock signal. So this processor requires memory access during the low cycle. So what happens is during the cycle, the earliest stage, at this where address is available in this cycle and the data is available in this cycle. So you see that during this time address is put on the address bus, and in this time at the end of this clock the data is read from there. Okay. So now let us talk about different bus cycles. I mentioned about sequential and non-sequential. Let us see what they mean. A non-sequential cycle requires the transfer to or from an address which is unrelated to the address used in the preceding cycle. What I mean by this is that suppose you look at the address bus and the data bus. There is one address coming out of the processor, goes to the memory, and the data is given out by the memory. Now next address is coming. If this next address what is coming out of the processor is not related to the previous address, that means they are not sequential. Okay, the random addresses coming out of the processor. There is no relationship between one and the previous cycle, and memory decodes every address and then puts the data into the bus. So this is called a non-sequential cycle where there is no relationship between subsequent addresses coming out of the memory cycle. Now in the sequential case, what happens is when you need to read sequential bytes or words from the sequential locations, the processor can put the addresses, increment it one by one based on the word width, whether it is being a 32-bit transfer or 16-bit transfer, and it will also indicate to the processor that it is a sequential address. Now what is the advantage? Once the memory knows the requests that are coming out from the processor are all going to be sequential, then the memory could be ready with the data, because it knows that if it is the processor is reading an at 1000 and the width is 32 bit, then it knows that the next request is going to be from 1004 and the other one is going to be 1008. So memory can prefetch the data internally without waiting for these addresses to come from the processor, so that it can complete the cycle much faster. So the sequential addresses are relatively faster than a non-sequential address. Now what is internal cycle? Now, as I mentioned in the CPU diagram, where we saw the processor core sitting, and then there are so many co-processors and other cache and memory management units in a single chip. Now the same data bus and address bus coming out of the processor core is not only connected to the memory, it is also connected to the co-processor, or it could be connected to some other units on the bus. So when the processor is intending to do some transaction between itself with the other co-processors, it doesn't want any interruption or anything driven by the memory on the bus. It has to indicate to the memory that I am doing something other than talking to the memory. So that is one way of informing the processor that it is not communicating with the memory now. This cycle is going to be used for something else. So this is one scenario, and another scenario could be that the processor is busy doing some operation inside. It could be doing MAC operation or some other arithmetic where it cannot use the address data bus for fetching either fetching an instruction, or it is not using the bus for accessing the memory. It could say that it is in the internal cycle mode. So these two are the different modes. The coprocessor mode is for informing that it is performing a coprocessor transfer, and internal cycle is for saying that it is busy with the internal operation and it cannot do any prefetching at this time. So these are the four modes. So if I ask you which are the modes where memory should not drive any signal onto the bus, it is very clear in both these modes, because internal acts as coprocessor register mode, it is nothing to do with the memory. The processor is talking to either coprocessor or it is busy with the internal operation. If the processor is doing a transaction on the bus using this cycle, that means it is communicating with the memory. Either it could be non-sequential accesses or it's a sequential access. So based on that, memory can respond according to the address which is coming out of the processor. I hope these four different types of cycles are understood by all of you. Now, how is it communicated? This is the way the signal, the combination of this mention, this is coming out of the signal. Okay, based on this, you can see that whether it is given by the processor or it is coming as an input or output to the processor. This is an output from the processor to indicate that it is doing one of these cycles. If it is doing N or S, it wants the memory to be active. So this, as I said, MRAC bar is 0 is active. So this means that memory needs to be active to take care of the decode the address and drive the data buses. But if it is 1, memory just shuts off and the processor is free to communicate either with the coprocessor or it is free to do whatever is internal operation it is doing. So non-sequential is the simplest form because no relationship between multiple addresses coming out of the processor. And sequential, this is a burst mode. As I told you, first address is given and then it says that I am starting a sequential cycle. That means it is going to access the memory starting from this address to subsequent addresses. So till this sequential mode is changing to non-sequential or some other cycle, either it's the process, internal cycle or a coprocessor cycle, it will continue to read from the sequential addresses starting from the addresses. But one thing you have to remember that every cycle the incremented address is also put on the address bus. Okay, but memory can comfortably go and do the data access because it knows that the processor is interested in sequential address access. Okay, so whether address is incremented either 2 or 4, So you may wonder why there is no incrementing by 1. The reason being ARM doesn't support a byte sequential burst mode. It doesn't make sense, you understand, right? 1000, suppose a processor wants to access only a byte from the address 1000, then the next address will be 1001, 2, 3, 4. So when the processor could read all the bytes in one cycle, by saying that I am reading a 4-byte value from memory, if it is trying to do a byte burst transfer at byte level, it's a waste of effort, waste of time, as well as waste of power. So normally, then you may wonder why is this half word is supported in the burst mode, because we may have a system where the memory that you are having in the system has only 16-bit data. Okay, the memory is a very cheap memory with a low cost application. So we can't say that ARM software CPU cannot work with the memory which has got only 16-bit data. So ARM has provided that provision that half-word transfer, through half-word transfer, it can talk to a memory with a 16-bit data bus, and it has to perform any operation, all the operations of the memory only in the half-word mode, and it could perform even burst transfers with the memory if the memory controller supports. Okay, and memory system can even often respond faster, as I told you. In the sequential access, memory system can respond faster. Okay, now let us see what is internal cycle. Now I have already explained to you, this is something to do with operation performed by the processor internally, and it doesn't want anything to be activity to be happening on the address or data bus. So no prefetch is required, and so processor doesn't do any operation. But at the end of internal cycle, it can broadcast the address to start the next memory cycle. So in preparation for the next memory cycle, it can broadcast the address, and memory will decode that, but it won't drive the address data bus until a memory cycle has started. Maybe the next memory cycle could be a non-sequential access or a sequential cycle, but anyway, when the new cycle starts, address will also be coming, but the memory has got the address ahead of the cycle, so it can do the decoding and then ready with the data ahead of time. So that's a provision provided by this particular support. So coprocessor register, as I told you, that there could be a coprocessor connected to the processor, and the transaction may be between the coprocessor and the processor. So memory needs to be discontinued, or it should not drive any signal on the bus. Okay, so these are all the details about bus selectors. Now let us see what the reset signal is all about. This is N reset, that means if it is low, it is a reset signal is coming out. Processor needs to take action. So normally the reset signals are driven by a RC circuit. Now a low level causes the instruction be executed to terminate abnormally. So you know that when the processor is running, suddenly somebody comes and resets the board. Whatever is happening on the instruction execution is happening on the processor needs to be terminated, and then the processor needs to start from a known state. So that's the intent of reset. Or when the development board or the system that you have with the ARM core running, and you switch on the system, when it powers on, the ARM has to come up with in a known state. So the reset could be either the processor is running, in between somebody has given a reset signal, or it is powering on for the first time. Whatever may be the situation, the ARM core needs to start from a known state. So the reset is very important, and that's the first thing what we all should know. What is the behavior of a processor when a reset is given to it? So as I told you, N weight should be high for the N clock signal to be used right away. Otherwise, if you hold the N weight as low, then the clock is held low, and you have that stretching the signal. Okay, the clock is slowed down because of that. Now, the supervisor mode. I will not talk about the supervisor mode now. In the subsequent, within the few seconds, I will be talking about that. This actually. This is the mode in which the processor starts to begin with, and I will talk about branch registers before we say what is the speciality of supervisor mode. Okay. Now let us go into a register step and the different operational modes of the processor. Now this is the registers that normally as a user we would be using. So these are all 32-bit wide registers. They are called R0 to R15. But these three registers which are shown in shadow and no, they are all for special purposes. We'll see what they mean. And CPSR is the current processor status register, which has some conditional code and means about some internal operations. Okay. So there are 16 data registers and one status register. R0 to R13 are orthogonal general purpose registers. What it means is that these orthogonal means any instruction that you can do with R0 can be done with any other register. So suppose if there is an add instruction and you say that R0, R1 to R2, you could also write it as R5 to R6 to R7. So these registers can be used, in the instructions where one of them could be used. That means these registers can be, you can comfortably use them based on which is occupied by some other value and which one is free for you to use the registers in your assembly instruction. Now what is the shaded registers identify? They identify some special purposes. I talked about a lot of things about stack. So in the previous discussion, so R13 is traditionally used as a stack pointer, and especially if it is used with if the processor is OS is running on the processor, then the OS operating system will assume that R13 is dedicated for the stack pointer. If suppose you are writing your own code, you are free to do anything you want because it's part of a set of orthogonal registers. But especially if you need to connect to another library or some OS code, better not to use this R13 for some other purpose, general purpose. It should be reserved for stack. And R14 is a link register. I can give you just brief example of what it means. Suppose there is a subroutine call. We will talk about those things when the instructions we talk about. So if a control is moved to some other place through a subroutine call, the return address where after subroutine is executed, where the processor control has to come back, is actually available in the PC because PC is implemented from the current instruction. So that return address is actually saved in the link register, so that on return from the call, the return address could be copied back from R4 to R14 to PC, so that the processor comes back to the instruction just after the subroutine call. Anyway, we will talk about this later. Just I thought I will give you some overview of what it is. R15, as I mentioned, this is the program counter where the next instruction to be fetched is always pointing at. So R15 is pointing at the instruction to be fetched from the memory. Now CPSR is the current program status register. Let's see what they contain later on. Now program counter, as I told you, this is a 32-bit wide. Because all ARM instructions we call ARM state because it is not in thumb mode, it is called ARM state. Okay. So in ARM state it will be accessing 32-bit instructions. So the PC will be pointing at set of 4 bytes, whereas if it is in thumb mode it is 16. Now when I say that it is pointing at set of 4 bytes, it is always accessing the instructions as a 32-bit bit. So as I mentioned in the previous discussion about memory interfaces, if it is accessing an instruction from the memory, the code, the instruction is read in always as a 4-byte data. So 4 bytes is no instruction. So if it is reading as a 4-byte, then you can assume that the least 2 bits, the bit 0 and 1 are always 0. And it is mandatory that all instructions are 4-byte aligned. That means no instruction can start on odd boundaries. That means suppose you take an example of 1000, 1001, 1002, 1003. These are all different byte addresses. Instruction can start only from 1000 or 1004 or 1008. You cannot put an instruction starting from 1001 or 2 or 3 because always the processor reads from the memory all the instructions which are 4-byte aligned. So it expects the instruction to be 4-byte aligned. So that means the PC will always give these 2 bits 0. So non-constant bits are only 31 to 2 bits of a R15. So usage of R15 instruction, suppose because it is little different from ARM processor, it is different from other processors where it is even the PC is part of the general purpose register set. So you can use PC also as one of the operands for the instruction, but it has to be used with the caution. Whenever we talk about instruction, I will touch upon those things which you need to take care from the perspective of using the R15 as a general purpose register. Okay. Now conditional flags, we have talked about this earlier. What are the things, when some binary operation is done, how these flags are set, we understood. Now this is the place it occupies in the CPSR register. So the MSB 4 bits are mapped onto this flag. Now these are all left unused, and we'll see what all these other bits mean. So normally any processor, there will be some bits reserved for future use, so that the processor can be extended with the next family of ISA, and new instructions can be added, new conditions can be added. So these bits are left unused. They are divided into 4 states, 4 classes. The condition flags, of course, mapped onto these flags. So negative, 0, or carrying the overflow flag. As you know, overflow flag is for signed arithmetic. Now let us see what is this interrupt mask bits are for. I told you that interrupts are always generated. It could be from internally also, but any external interrupts coming are connected to 2 bits of the control pins of the processor. So they are IRQ bit, which is coming into the processor. So if this IRQ, this particular I flag in the CPSR is set, that means even if there is an interrupt coming from the external system, it won't be recognized by the processor. So suppose if you want to disable the interrupt, you want the processor to be not to be interrupted because you are doing some critical job, and hopefully it is not right for returning, then you can disable this interrupt flag by setting these bits to 1. Then no interrupt will be recognized by the processor. Same thing for FIQ. FIQ is a fast interrupt. You may wonder what is the difference between these two. Actually, the priority of this is higher than the priority of this. That means you can connect any interrupt from any source which needs to be attended to without any delay. That interrupt has to be connected to this particular input, and any other serial port or any USB or any other devices where it can afford to wait for servicing this interrupt, it can be connected to IRQ. So internally, when both the interrupts come into the processor, the FIQ interrupts are given higher priority. This will be serviced first before coming into this interrupt. Okay. Now, what are the processor modes? This is a very important concept you should understand. So these 5 bits, the lower 5 bits of the CPSR correspond to the processor modes. It could be privileged or non-privileged. All of you must be aware of, would have done some course on operating system. So there are privileged and non-privileged states in the processor, the user mode or kernel mode. So the privileged mode is basically it's for operating system or some supervisor mode. Non-privileged is for a normal usage, normal users program to run on the processor. Now you can understand that compared to this, privileged mode has a higher privilege, right? So in the privileged mode, they have access, full access for read and write of the whole CPSR. You can change anything. If the processor is in this mode, they can go and modify any of these bits in the CPSR. Whereas in the non-privileged mode, the user who is in non-privileged mode has only read access to the control key. It can know the current mode, what is the current status of these, whether the interrupts are masked or not, whether it is in some mode or not, what are the flags set by the processor. But in the non-privileged mode, you cannot modify any of the bits in the CPSR. Okay. Let us see. Now, what are the different modes supported by the ARM? Now, except the user mode, which is in the top, all other modes are privileged. Okay, that means in these modes, the CPSR can be modified. Now, this also has additional feature. When I say that in the privileged mode, the CPSR can be modified, here in this mode, another register which is called SPSR, which is called saved program status, is also made visible to the program. That means I'll give an example. Suppose a processor is running in a user mode. Okay, assume before getting into the user mode, some supervisory code was running, and then it has enabled the FIQ bit in the CPSR. That means if any interrupt comes, the FIQ interrupt will be processed and it will go to the service routine in the ISR. Okay, I'll not, let us not worry about how the service routine is run now. We will talk about the interrupts later. But suppose if the processor is moving from the user mode to fast interrupt mode because of an interrupt coming, it will have a visible another register called SPSR, where automatically the CPSR is copied into the SPSR register. Why is it done? Because when it is changing from user mode to fast interrupt mode, the original mode value was actually referring to the user mode. Now, when it is in the fast interrupt mode, it is going to be changed to fast interrupt mode. So you have to have the old content of the CPSR, because even in the user mode process, our program would have been running, and we may be performing some additional or arithmetic operation, and the conditional flags would have been changed. But when it is entering the FIQ, it may perform some arithmetic operation, and those conditions of the CPSR flag would have been overwritten. Now, after the interrupt routine, when you come back, you will not get the same state of what you had prior to the interrupt. So, to achieve that, what ARM has done is it has made visible another register when they are entering into this mode, and automatically the hardware takes care of copying it. So, this I am telling you right now to just make have an idea of why SPSR is needed. But we will talk about it later on in detail. Okay. Now, apart from user mode, you see that there is a system mode also, which also has the same set of registers as user. There is no special set of registers. These are all. I'll show you what are the special set of registers which become visible in these different modes. But in the system mode, the only difference is that it can change the CPSR content. So, what is the use of that? I'll explain to that. So, in the subsequent session. Okay. So, the processor mode can be changed by a program that writes directly into the CPSR or by hardware when the code responds to an instruction. Okay. So, when the mode, so you may wonder, when is the mode changing? How the mode of the processor can be changed? The least 5 bits. It could be by any interrupt coming. So from the interrupt, it will know that okay, this is the interrupt coming from the signal. So automatically it will be set, or it could be done by the user program. Okay. Now you may wonder that there are so many registers now. I showed you initially that only these registers are there in the processor. We talked in length about this processor. Now we are seeing a whole lot of registers. Please understand that the registers which are shown with this here are the special registers which are visible. So, if you ask me physically how many registers are there in the processor, forget about which mode they are in. Physically, there will be 37 registers. Means you have to add up all the shaded portion and the user mode registers. It will all be 37. Now, again, let us go back to the old example of from the user mode you come to FIQ mode when on interrupt. What happens is suddenly during this FIQ mode, this register is visible, and you get a new set of registers which are this 4, no, this 8 register, we have the 7 registers. Now what happens to this? Actually, in the FIQ mode, if you say R8, it will be accessing this, not this register. Okay, so in the FIQ service routine, if you write move F8, 100, the 100 is written into this register, and original content of this will not be displayed. So based on the mode in which you are, you will be accessing those special registers with this name. Now what happens to this register? They remain the same. So it is same as this register. So physically only one set of these registers are there, but they are shown multiple times because in each mode, each mode you see the register is what is shown here. So what is the advantage of having so many registers in FAQ mode? Because you don't have to, when you are jumping into the service routine, you don't have to save this content because you are getting a new set of registers here. In the ISR, you can use them and then come back without interrupting the normal flow of program. So that is the implication of these registers, where you say that these are different banks registers are available in ARM. So all custom modes except system mode have set of associated bank registers. So what I said was, in system mode, the bank registers map, okay, are same as user register, and their bank register map to user mode register. When the processor mode is changed, the bank register from the new mode replaces an existing register. Okay. So for an example, on the interrupt request, if suppose R13 and R14 are accessed in the new interrupt in IRQ, they will be accessing the R13 and R14 of IRQ and not the original user mode register that I explained you earlier. So user mode register R13 and 14 are not affected by this operation. Okay, whereas R0 to R12 in IRQ are same as a user mode register. So what is the registered bank? Register bank is a whole register file. Whatever I showed you on different registers, different modes, all those registers are called as a register file. So the ARM7TDMI processor core has additional features to enhance the performance. What are they? The register file has 2 read ports and 1 write port. What do I mean by this? That means in the same cycle, 2 registers can be read simultaneously. Okay, and 1 register could be written into. Okay, so typically if there is a 1 register and then there is only 1 port available, 1 read and write port, you can either write in 1 clock or read from the register in 1 clock. But if the whole register file is given multiple 2 read ports and a write port, you can do 2 operations at the same time. You may wonder why is it required. If you remember the operands that are required for any addition or subtraction, there are 2 operands needed, right? So those 2 operands could come from 2 different registers which are in the register file. So you may say that add R0, R1, R2. That means you are taking 2 parameters R1 and R2 from the register file, and because register file has 2 read ports, both the operands R1 and R2 operands can be read from the register file simultaneously in single cycle. So that's why ARM has provided this multiple ports. And if you remember that R15 is also part of the register file, and it is a special purpose. So it's a program counter. Now you know very well that when the program has to execute, it has to increment the program counter and keep on accessing the instructions, subsequent sequential addresses from the memory. Now where it has to be written into? It has to be written into R15, which is part of the register file. So to enable incrementing or changing the value of our PC, irrespective of without any interruption happening to the operands being read from the register files, ARM has provided 2 additional ports only for R15. What does it mean? For accessing the R15, you can use these ports. So these ports allow reading and writing of R15 independent of any read or write happening on the other registers in the register file. So they can happen in parallel. So effectively there are 3 read ports and 2 write ports, but one is very unique and special that it can be used only for accessing the program counter. Why we need to access the program counter every cycle? Because every cycle, every instruction being executed, the program counter is modified because it has to increment to the next instruction. So that means the program counter has to be written into with a new address. So we need a separate port for that, so that instruction can keep on modifying the R15 without affecting the data accesses from the other registers in the file. So this is what happens. The last bullet shows that you can update the R15 without any issue. So now let us see what are the special mode, privilege mode registers are for, and let us take an example. This special registers like stack pointer and link registers are for 2 bank registers. Okay, this is used for holding the stack pointer and return address. So why do we need special registers for every privilege mode? Again, coming back to the example of fast interrupt. When fast interrupt happens, any interrupt happens, it is going to another routine and then it executes the whole set of instructions. So when it is using up some of the user registers, it has to save those registers into stack. So we need a special stack for the interrupt routines, right? So it can point to a different memory location in the memory, and the saving and restoring of registers can happen with those stacks. So each of privilege modes can be initialized with different stack addresses, so that they can all point to different stack addresses, so that any saving of registers could be done based on the mode etc. We will talk about this in some more in detail in the subsequent lectures. It is better if you understand that it is needed, it is provided for the sake of saving the registers which are used by those privilege mode functions. Okay, the exception handlers. But FAQ is given additional registers because it doesn't have to save those registers, because it is getting those set of registers, so it can perform the operation much faster than the rest of the privilege mode exceptions. So as I told you, when the CPSR contents are modified, the new registers become visible based on which privilege mode is written into the CPSR. And the R14 is a link register which preserves the PC value before the exception or the interrupt has happened, and then so that it can be restored from this value. It can come back to the instruction after the exception which is to be executed. Okay, so let us see what reset does. After the end reset was made, see how a reset is given to the processor. It has to be made low, okay, and then dot high. Now I am coming back to reset because earlier I couldn't explain you about what are the different modes available. So now, having understood different modes are there and they have a special registers reserved for each of the modes, now you can understand and relate why on reset mode the processor need to enter the supervisor mode. So when reset is given, okay, either because of power on or it is given forcibly by some external circuitry, the processor enters the supervisor mode. What does it mean? The LSB 5 bits of the CPSR is made as 1001, which corresponds to supervisor mode. If you recall, I told that supervisor mode has the same set of user registers, okay, but it has got access to SPSR as well as it has got its own SPSR as well as it has got a write access to the CPSR. Okay, so what happens is on reset, whatever may be the value which is saved in R14 and currently what is there in the CPSR is copied into these two registers, because it is getting two additional R14 SVC and SPSR SVC in the supervisor mode. So it saves the current address. So current okay value, actually this must be a PC to R14, okay, and then disables IRQ. It saves the PC value and the CPSR, current PC value and the CPSR value to SPSR, and it disables this interrupt. So on power on, on reset it makes sure that no interrupts are enabled, and then it clears C bit. That means it is going to start in ARM mode, not in thumb mode, and then the PC is loaded with a new value. So actually this has to be corrected as PC. Okay, so PC is moved into this. So current PC wherever it is moved into this. Maybe it could be used by later on for debugging purposes. They know when was the interrupt given. So, but if it is in a power on, they are having unpredictable values. So they are saved into this register, and then the PC is loaded with a new set of value, which is the 00016. So actually, program ARM processor starts executing from this on reset. Okay, so this is the reset behavior. It gets into supervisor mode and then comes back to normal ARM user mode and starts executing from 006. But it saves the PC value and CPSR into these special registers, which are bank registers in the supervisor mode. So this is the purpose of supervisor mode, and this is also used for operating system routines. When if suppose OS is also running on your system and your user applications will be running in user mode and OS code will be running in supervisor mode. So after reset, all the register value except PC and CPS are indeterminate. Okay, so this is the now we have come to the end of the class. In this section, we learned about what is the processor core and CPU core, what are the interface signals. We talked about the multiple data buses available and what are the different signals available to interface with the memory and different transfer sizes possible. And then we talked about bus cycles, which is sequential access or non-sequential access or internal cycle, or it is a co-processor cycle. So we talked about this, and then we understood about register set where bank registers are there, and based on the lower 5 bits of the CPSR, different modes are decided, and based on the mode, different bank registers become visible, and there is a special saved process state register which is used for saving the CPSR content into them. So, and then we talk about reset. On reset, when the processor enters the supervisor mode and then saves the PC value and current CPSR value into SVC special register, and then it starts executing from the address 00. So with this we stop this session, and hoping to see you in the next session to learn more about ARM architecture, and we will be covering the instructions, and before that we will talk about pipeline support in the processor in the next section. Have a nice day. Thanks for listening. Take care. Bye.